Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to go over Leetcode 636 exclusive time of functions, and after a tricky variant. Let's get started. Normally, I read the whole problem description, but I'll tell you right now, it's not only verbose, but it's also very, very confusing. Allow me to summarize. We're given a list of logs, in which each log represents a function call on a call stack. Naturally, we ask, what do these colon-separated strings mean? To help answer this, let's visualize these logs a little bit better. Going through what they signify, our first log is a function call whose ID is 0, and it started at a timestamp of 10, as you can see. During this invocation, we call another function whose log represents the start of another method. Its ID is 1, and it starts at a timestamp of 20. This currently invoked function will end, and that's because the following log says so. We know this for sure because it has the same ID of the 1, and it ends at a timestamp of 50. It should be noted that we'll only ever be given logs that start and then end. Those are the only two values. From here, we return back to the original function where we observe the last log. It denotes the end at a timestamp of 60 for a function whose ID is 0. Okay, that makes sense to me. Next up, what is our objective, you ask? It's to return a resulting list that represents the total amount of time each function took. The desired output type is very particular, so bear with me here. They want a list whose indices correspond to the function ID. So here is the 0 for 0, and likewise 1 for the function 1. And the values map to the exclusive time of each function. So for function 0, it's 20. As to why, it's because it took 10 units of time from here to here, and another 10 units of time from here to here. 10 plus 10 is indeed the 20. For function 1, it's 31, because the time that the function ended at 51 minus the time it started at 20 is the 31. And no, I did not misspeak. This is part of the requirements. That when we're told that a function ends at a given timestamp, it means it ends at the timestamp plus 1. For proof, check out this terrible requirement. The timestamp ends at the end of its timestamp. I hate it. I hate everything about it, but that's how it be sometimes. Building on this may be a cause for further confusion. Why does function 0 only consume 20 units of time, not 21? We note that it ends at a timestamp of not 60, but 61. We minus this by 51. Remember to get 10. Thus, because both of these ended in an off by 1, their difference is as if we never had the plus 1s to begin with. Very, very confusing. We should also note that we only get this awkward off by 1 when the function ends, not when it starts. This means in terms of this excerpt right here, there's no funny business. We simply do the 20 minus the 10 to get 10. Altogether, 10 plus 10 is indeed the 20. And ultimately, this is our answer. This is what we return. Now, how do we solve this programmatically? For one, functions get pushed and popped off the stack all the time. Why not a literal stack? The problem description implies that the logs will always be formatted correctly. Put another way, the start of a function will always match up nicely with its end. If it helps, think about these logs as valid parentheses. Or not if it gives you trauma. Okay, that's enough intuition. Let's just YOLO this example with our stack data structure and see where it leads us. On the first iteration, we have the beginning of a function call. Let's just mindlessly throw the kitchen sink at our stack. Specifically, an ID of 0, a type of start, S for start, and a time of 10. Moving on, we'll do a similar push for this next log. Function 1 has been called in the middle of function 0, so let's split up this log into 3 parts and push them onto our stack. Next up, we observe a new scenario. We have the end of function 1. I don't know about you, but I see an opportunity to count the amount of time function 1 took. We can find the delta between the timestamp of 50 plus 1 and the most recently pushed element on our stack, which so happens to be the start of the method, right here, remember. Doing so means we can successfully compute a time of 51 minus the 20 to get 31. We'll add this exclusive time at an index of 1. Thankfully, we have this function ID available to us on the stack. So we have everything we need. The function ID serves as the index for us. This is correct. Since we exhausted function 1, it literally started and then ended, we can safely pop it from our stack. That's the end of that iteration. That logic sounded flawless. I'm sure nothing will go wrong. On the last iteration, we have another end of a function, function 0. Let's do the same thing, compare it with the next most recently pushed log. What's 60 plus 1 minus 10? That's 51, and that is actually not correct. Function 0 obviously did not spend 51 units of time. There was a literal gap in the middle where another function, function 1, was invoked. So it turns out our logic is flawed, and we must account for this. But how? Let's be a bit brainy and think back to what did work. Namely, for function 1, when it had ended, we accurately looked back to note the very start of the function. We showed off some middle school math and calculated 51 minus 20 to get 31. Let's attempt to replicate this logic everywhere else, where early on in our logs, when function 1 had started, can't we look back at the previous log of the start of function 0? We'd have the 2 timestamps we need to compute 10 units of time. Same deal for the only other iteration. When function 0 runs its course, we'll look at the previous log, which is this 51, remember. To be exact, we can minus a timestamp of 61 and 51 to get 10. And indeed, these are the exact numbers we need to add to our resulting list. To be a bit closer to the code, we'll actually make this prev number a first-class citizen into its own dedicated integer variable. This idea may lead us full circle and ask, if we're always looking back 1 to figure out the computation, then why can't we just look at the topmost of our stack? To re-explain, the last iteration is a perfect example for why we cannot. So if we were to look at the most recently pushed log on our stack, we get function 0 with a timestamp of 10. As we saw before, 61 minus 10 is just not correct. We'd fall into the same trap as earlier. Therefore, this won't work. Okay, overall, the logic sounds fine, but I have a question myself. If we're always looking back at the previous log, it makes me question, what about the very first log? Clearly, there's no log before that, and we definitely don't want to count another unit of 10 for function 0, because it literally never happened. Therefore, we'll only count the exclusive time of a function if we're not on the first iteration. Simple enough. All right, wow, so many good ideas. Let's pull them all together in a more sizable example. All right, here's our daunting test case. As always, we're given a list of logs, but additionally, we're also given an n of 4. This tells us ahead of time that there will be a total of 4 functions. 1, 2, 3, and 4. This is necessary to be able to instantiate a result list of the 4 unique functions. And no, we can't tell how many functions there are given a list of logs. Sure, it works in this example, where there are 8 logs. Every function must start and end, right? Thus, each function consumes 2 logs. 8 divided by the 2 is 4 functions. Fine, but let me prove by contradiction. It was mentioned in the problem description that a function can call itself, and thus be a recursive function. What if we were given something like this? Function 0, highlighted in green by the way, starts and then recursively calls itself. It's probably some nightmare DFS LeetCode problem, but thankfully it's not our main concern. Anyway, this recursive call starts and ends. It must have hit some base case. Returning to the original function, function 1, highlighted in pink, is then invoked. For all we know, this is backtracking logic. Function 1 terminates, and then we continue on in the original green function where it also ends. So, in total, we have 1, 2, 3, 4, 5, and 6 logs. 6 divided by 2 is 3. Does this mean we have 3 unique functions? Nope, it's the 2. 1 and 2. Alright, cool. So those are the inputs we're given. In terms of what variables we need, we have our result list, stack. That's right, one last thing, we need a prev variable, 0 initialized. This is our way of looking back and computing the exclusive time. Alrighty, we're readily equipped to walk through this example. On the first log, function 0 starts at a timestamp of 20. Recall our logic. To account for the amount of time a function consumes, we take its timestamp, of the 20 in this case, and minus it by the previous timestamp of 0. Just kidding, not on the first iteration. Function 0 just started and there's literally nothing before it. We know this to be true because our stack is empty. There aren't any logs yet. All we'll do for this iteration then is to add all of this logs metadata onto our stack. An ID of 0, a type of start, S for start, and a timestamp of the 20. Lastly, don't forget to update the previous variable to the 20. Moving on to the next iteration, we invoke function 1 that started at a timestamp of 30. Unlike before, our stack is not empty, meaning there's an actual previous log. We'll take a timestamp of 30, minus it by a previous of the 20 to get a duration of 10. Function 0 has run for that long. We'll look up in our resulting array with an index of 0 and add 10 units of time. Thank goodness for our stack here. That's how we're able to reference the function ID of 0. Fantastic. There are 2 more orders of business. Let's push the metadata of function 1 onto our stack. And remember to update previous to the current timestamp of 30. Afterwards, we note function 1's end at timestamp 40, or in reality, 40 plus 1. This means we know function 1 lasted 11 units of time, or more mathematically, 41 minus a previous of 30 is 11. We'll look up the ID of interest from the topmost of our stack and add this duration in our result as appropriate. Let's also pop from our stack because function 1 clearly finished, literally. We no longer have a need for it. One more thing, let's reflect the new previous time to not 40 but 40 plus 1. Right after function 1 ended, function 2 was invoked at a timestamp of 41. We take this 41 subtracted by a previous of 41 to get a duration of 0. And it's true, function 2 started right after function 1 ended. So we'll look up an ID of apparently 0 from our stack and add this 0 to function 0, nothing changes. The part that's kind of odd to me is the fact that we looked up function 0's ID. I suppose that's because we pushed and popped our ping function that started and ended. But in these cases where an immediate new function is invoked, we'll always have 0 units of time, so I suppose there's no harm for our logic. But anyway, some house cleaning. We have a new function that started, so let's append all that metadata onto our stack. As well as update our previous variable from 41 to 41. It remains unchanged. Okay, let's zoom through the rest of this example. We have function 3 that started at a timestamp of 50. We'll find the difference between 50 and 41 to get 9 for function 2. That is correct. We'll add 9 units of time as appropriate. To end the iteration, as per usual, we'll append the ID, the type, as well as the timestamp, and then update our prev time to the 50. Next up, we observe that function 3 has ended, so let's account for that. It ended not at 55, but 56. We'll minus it by 50 to get 6 units of time. We'll get an ID of 3, which acts as index 3, and add 6 to it. Since function 3 started and finished, we're done processing it. Let's pop it from our stack. Remember to reflect the new previous timestamp in our variable, 55 plus 1 of the 56. From here, the two remaining iterations are quite similar. We return to function 2 that then ends. We'll do some math. 61 minus 56 is 5. And it's true, function 2 did last for another 5 units of time. We'll look up its function ID and add 5 to its exclusive time. What's 9 plus 5? It's now 14. The function ended, let's pop it, and update the previous time. On the last log, we note that we return back to the very first function. It terminates at 101. We see how long it lasted. 101 minus 61 is 40. We peek in our stack, find an index of 0, look that up right here, and add 40 to 10. That gives us 50. Don't forget to pop from our stack and update our previous variable one last time. Amazing. This is our answer. This is what we return. I just have one note. When we looked at our stack, we only looked up what the previous function's ID was. Inversely, we didn't care about the timestamp because we already had the previous variable, which is more accurate and correct. Furthermore, we had no usages for the type either, whether it was start or end. We already obtained this information because of the logs we're literally traversing over. What I propose then is that we obliterate these two fields. Great. With that, the time complexity is big O(n) because of our singular for loop. And the space complexity is also big O(n) because of our stack. Technically, it's a bit lower than that because we only have the start logs in our stack, but it's generalized to big O of n. Okay, let's code. All right, let's spin up everything we need. This includes a resulting list, a stack, and a previous variable, all of which are initialized to a 0 initialized list of n functions, a stack that is actually a dec for efficiency, and a 0. Let's return result before I forget. We'll iterate over each log in our logs input. On each iteration, we'll split each log by the colon to extract the ID, type, and time. I didn't really mention this next part, but it was somewhat obvious that everything extracted is a string. That said, we'd like our ID and time to both be integers. Now we ask, did we have a function that started? If so, we'll calculate the duration with time minus previous, look up in our resulting list the ID, which remember is the only thing on our stack, to add this exclusive time to. From here, recall an edge case. We only do this if there was a previous time to begin with, or in other words, if the stack is not empty. Either way though, we started a function, so we'll push the ID and adjust the previous time. Now, what if we inversely had a function that terminated? We'll similarly take note of how long the function ran for. Please compensate for the off by 1 and add it to the appropriate function. Quickly note the fact that we popped the function off the stack as well. It's been entirely processed. Last thing to do is to update the previous timestamp to the current timestamp plus 1. You know, because the function had ended. Good job. The variant is subtly different in many aspects, but in my opinion, makes the problem slightly easier. Let's take a look. Welcome to the variant, where everything you know changes by about 10%. Not that much, it doesn't upset me. Reading the problem description, we are tasked to profile the performance of an application. Specifically, we're given a list of logs representing the execution of function calls in a single threaded application. Each log records the function name, the event type, so start or end, and the timestamp of when the event occurred. Like before, a function's exclusive time is defined as the total time it spends executing, excluding any time spent in its subroutines. Write a function called profile app that takes in a list of logs and returns a dictionary mapping of each function name to its exclusive execution time. You may define the schema of each log however you choose. Okay, that was a doozy. But to spell out the differences, perhaps the greatest one of them all is that there is no longer an off by 1 error. You can gloss the description if you wish, but there is no mention of it. In the original problem, if a timestamp supposedly ended at 50, then it actually ended at 51. But now, 50 means 50. That's a win in my book. Secondly, you'll notice the input has changed, or more accurately, has become more ambiguous. You may define the schema of each log however you choose. Taking a step back, in the original problem, each log was a string of 3 fields. But now, since we wield the power to dictate the schema, why not deserialize this string into a strongly typed object, perhaps called log, with the function name and type as strings, and the timestamp as an integer. I feel like this also makes our lives a bit easier. On this note, functionally, it'll be the name that serves as the unique identifier now, not the ID. Thirdly and lastly, it was subtle, but note the return type also differs. It's no longer an integer array anymore, but rather a dictionary from the function name to its exclusive time. To me, this is more descriptive and usable than an array, whose indices are the IDs, but in all honesty, I actually don't have an opinion for one over the other. These 3 twists in requirements do change the implementation ever so slightly, and being able to adapt in real time during the interview can take some time. Let's go over a quick walkthrough to make sure we understand everything. Let's get started. On the first iteration, we call a function named foo at a timestamp of 10. Being on the first log and all, there is no exclusive time to calculate, so we'll skip any math computation. We will, however, append the function name onto our stack. Recall, it's the name that's the identifier now, and like before, we don't have any uses for the type or the timestamp. Minmer headquarters has no room for bloated code. One more thing, let's update previous to 10. In the second log, we observe we call a function called bar from our function foo at a timestamp of 20. Great, we have an opportunity to account for this duration. What's 20 minus the 10? It's 10. To include this exclusive time in our resulting dictionary, we'll insert it with a key of foo, found on our stack. Since we have a new starting method, let's append its name onto our stack. And lastly, it's easily forgettable, but let's update our previous to the current timestamp of 20. Moving on, we see that function bar has terminated at a time of 50, not 51, but 50. Thank goodness. How long did this function run for? It's the 50 minus a previous of 20 to get 30. To track this, we'll insert a key of bar and the 30. Since bar has ended, we'll pop it from our stack and reflect the current timestamp in our previous variable. We're almost there. On the last log, we return back to our foo function, where we'll eventually terminate at a timestamp of 100. As per our routine, we'll minus 100 by a previous of 50 to get 50 units of time. Indeed, foo ran for another 50 seconds, minutes, whatever. So what we'll do is look up a key of foo in our dictionary and add 50 to what's there. 50 plus 10 is 60. Let's write that down. We'll then pop foo from our stack and update previous to 100. Not that it matters because we're on the last log, but we're very rule-oriented people. This is our answer, and this is what we return. Nothing unexpected. The time complexity and space complexity remain the same as the OG problem. They're both big O of n. Okay, let's write this up. Before we implement any functionality, let's define our class. This is up to you. Do whatever your heart desires. But for me, I'll define a name, type, and time. We'll initialize them one by one. Now we can write our function. Name it profile app, and it'll take in our logs, which is really a list of our log type. We'll begin our functionality like the original LeetCode problem. We'll instantiate a local result, stack, and previous. The result is now a dictionary from function name to integer. The stack is actually a dec, and previous will be 0 initialized. But don't worry, it'll be changed on the very first iteration. We'll loop from log to log, and for each one, if the log type is start, then a function has begun. Now, if the stack has elements, which means it has previous logs, we'll access our dictionary at the specified key, the function name, and add to it the log time minus the previous time. 2 more orders of business, we'll append the function name to our stack, and then update the previous time to the current timestamp. Now, in the case that a function ends, we'll similarly look up in our dictionary the function name, but also pop it from our stack, and add to it the time spent in that function. We'll always update the previous timestamp. A slight refactor, whether a function started or ended, we'll always update the previous time. So let's extract that. I almost forgot. Let's return our resulting dictionary. And that's a wrap. Thanks for navigating the variants with me. Thanks for your support, and if you learned something today, please make sure you like, comment, and subscribe. Thank you.